Good morning all. Today we have topic backpropagation in neural networks in machine learning subject. Now we have a question, that is what is backpropagation? Backpropagation is a supervised learning algorithm for training multi-layer perceptron, that is artificial neural network. Backpropagation is the essence of neural network training. It is the method of fine-tuning the weights of the neural net based on the error rate obtained in the previous epoch, that is iteration. Proper tuning of the weight allows you to reduce error rates and to make the model reliable by increasing its generalization. Backpropagation is a short form of the backward propagation of errors. It is the standard method of training artificial neural networks. This method helps in calculate the gradients of the loss function with respect to all the weights in the network. Now next we have how backpropagation works, which is in simple algorithm. Okay, it is clearly mentioned that there are three layers. One is input layer, next one is hidden layer, so next one is output layer. In the output layer you can see the difference in the desired values coming over here. It means we need to go for the backdrop output layer. And why differences of the desired layer? Because the prediction and actual output, it just may have the differences. So all these, based on these differences, we need to calculate the error and we need to find the some error, and we need to apply the some loss function for the measuring the errors. So here we need to apply the backpropagation. So the point is coming over here, that is we need to go for the output layer and to the input layer, and this process is done by the backpropagation. So output layer, which is backdropping, is known as a backdrop output layer. Now we have why we need backpropagation. Most prominent advantages of backpropagation are: backpropagation is fast, simple and easy to program. It has no parameters to tune apart from the numbers of input. It is flexible method as it does not require prior knowledge about the network. It is the standard method that generally works well. It does not need any special mention of the features of the functions to be learned. While designing a neural network, in the beginning we initialize weights with some random values or any variable for the fact. Now obviously we are not a superhuman, so it is not necessary that whatever weight values we have selected will be correct or fits our model the best. Okay, fine, we have selected some weights values in the beginning, but our model output is very different than our actual output, and that is the error value is huge. Now how will you reduce the error? Basically what we need to do, we need to somehow explain the model to change the parameters, that is a weight, such that error becomes minimum. So let's put in it another way. We need to train our model. So one way to train our model is called as a backpropagation. So consider this diagram. Let me summarize the steps for you. Calculate the error. How far is your model output from the actual output? Minimum error. Check whether the error is minimized or not. Next one, update the parameters. If the error is huge, then update the parameters, weights and voices. After that, again check the error. Repeat the step until the error becomes minimum. Model is ready to make a prediction. That is the last step. Once the error becomes minimum, you can feed some input to your model and it will produce the output. I am pretty sure now you know why we need backpropagation, or why and what is the meaning of training the model. Now next question we have, that is what is a feed-forward network. A feed-forward neural network is an artificial neural network where the nodes never from a cycle. This kind of a neural network has an input layer, hidden layers and output layer. It is the first simplest type of the artificial neural network. Now types of backpropagation networks. Two types of the backpropagation networks are static backpropagation and recurrent backpropagation. Static backpropagation, it is a one kind of the backpropagation network which produce a mapping of a static input for a static output. It is useful to solve static classification issues like optical character recognition. Recurrent backpropagation is fed forward until a fixed value is achieved. After that, value or error is computed and propagated backward. The main differences between the both of these methods is that the mapping is rapid in static backpropagation while it is non-static in recurrent backpropagation. Now we have history of backpropagation. In 1961, the basic concept of continuous backpropagation were derived in the context of control theory by J. Cayley, Henry Arthur and E. Wilkinson. In 1969, Wilson and Ho gave a multi-stage dynamic stage optimization method. In 1974, Burgos stated that the possibility of applying these principles in the artificial neural network. In 1982, Hopefield brought this idea in a neural network. At the time, the neural network is known as the Hopefield neural network. In 1986, by the effort of the David E. Rumenhult, Geoffrey E. Hilton, and Ronald J. Williams, propagation gained recognition. In 1993, Wand was the first person to win an international pattern recognition contest with the help of the backpropagation method. Now, backpropagation key points simplifies the network structure by elements weighted links that have the least effect on the trained network. You need to study a group of input and activation values to develop the relationship between the input and hidden unit layers. It helps to access the impact that a given input variable has on a network output. The knowledge gained from its analysis should be represented in rules. Backpropagation is especially useful for deep neural network working on error-prone projects such as image on speech recognition. Backpropagation takes advantages of the chain and power rules allow backpropagation to function with any number of outputs. Now, what is backpropagation? The backpropagation algorithm looks for the minimum value of the error function in weight space using a technique called the data rule or gradient descent. The weights that minimize the error function is then considered to be a solution to the learning problem. Let us consider how it works with an example. You have a dataset which has a label. Consider the below table. Here we have the two columns. One is the input and the next one is desired output. So input values are 0, 1, 2 and desired output are the 0, 2, 4 respectively. So now the output of the model when the W value is equal to 3. So input value and desired value are given already into the above table and the model output will be the 0, 3, 6 respectively. Notice that the difference between the actual output and the desired output. So the absolute error in the above table, that is 0, 1, 2 and square error, that is 0, 1, 4 respectively. Let's change the value of the W. Notice that the error when the W is equal to 4. So absolute error and square error of the above table we have calculated. Now model output of the W is equal to 4, that is 0, 4, 8 respectively, and the square error of the model output, that is 0, 4, 16. Now if you notice, when we increase the value of W, the error has increased. So obviously there is no point in increasing the value of W further. But what happens if I decrease the value of W? Consider the following table. So as you can see, I am just doing W is equal to 2 rather than W equal to 3 or 4 as we have seen to the previous slide. So now the square error will be the 0, 0, 0. So it is good things we are decreasing the value of W. Now what we did here, we first initialize some random value of W and propagate it forward. Then we noticed that there is some error. To reduce that error, we propagated backward and increase the value of W. After that also we noticed that the error has increased. We came to know that we can't increase the W value. So we again propagate backward and we decrease the W value. Now we notice that error has reduced. So we are trying to get the value of weight such that the error becomes minimum. Basically we need to figure out whether we need to increase or decrease the weight value. Once we know that, we keep on updating the weight value in that direction until error becomes minimum. You might reach a point where if you further update the weight, the error will increase. At that time you need to stop and that is your final weight value. Consider the graph below. You can see that we need to reach the global loss minimum. This is nothing but the backpropagation. So let us understand the mathematics behind the backpropagation. How backpropagation works. Consider the below neural network as you can see over the slide. I1, I2 and these are the two input layer and H1, H2 these are the two hidden layers and O1, O2 are the two output layers. Each and every layer has its own weight. So if you can see the I1 to H1, so we have the weight 0.15 and 0.20, so W1 W2 respectively. Same we have the H1 to O1, so 0.040 W5 is the weight and W6 is the weight which is represented by the 0.45. So the above this network contains the two inputs layer, two hidden neurons, two output neurons and two vices as we can see. So V1 V2 are the vices 0.35 and 0.60. There are steps involved in backpropagation. Step number 1, forward propagation. Step number 2, backward propagation. Step number 3, putting all the values together and calculating the updated weight values. Now step number 1, forward propagation. We will start by propagating forward. So for doing this we need to calculate net h1 value, out h1 value and out h2 value. Net input for h1 value, which is recognized by net h1, so can be calculated by w1 into i1 plus w2 into i2 plus b1 into 1. So after putting all the values we will get the net h1 value, that is a 0.3775. Output of h1 can be calculated by out h1, that can be calculated by the 1 upon 1 plus e to the power minus net h1. So after putting all the values we will get the 0.59326 and same for for the out h2 we can calculate, or we can get 0.596884378. We will repeat this process for the output layer neurons using the output from the hidden layer neurons as an input. Now we need to calculate output for O1 values. So net O1 is equal to W5 into out H1 plus W6 into out H2 plus B2 into 1. So that can be calculated after the putting values. We will get the 1.105905967. So out O1 can be calculated like 1 upon 1 plus e to the power minus net O1. So after putting this value we will get the 0.7513657 as you can see over the slide. Same case before we can get the output for the O2. So our out O2 will be 0.7729284665. Now let's see what is the value of the error. Error of the O1 can be calculated by EO1 is equal to summation of half target minus output whole square, and which can be calculated after putting the values. So we will get the 0.2748111083, and error for the O2 can be calculated like the same process. So we will get the EO2 is equal to 0.0235600026. Then total error can be calculated by the E total is equal to EO1 plus EO2. So after putting the values EO1 and EO2, so we will get the E total values, that is the 0.2983711109. Next we have step number 2, that is the backward propagation. Now we will propagate backwards. This way we will try to reduce the error by changing the values of weights and vices. Consider W5. We will calculate the rate of change of error with respect to change in the weight W5. So here we have the formula with that is the partial derivation, and the partial derivation of E total with respect to W5. So we have the formula over the slide, you can see. Since we are propagating backwards, first things we need to do, calculate the change in total errors with respect to out O1 and out O2. So the E total we have calculated, that is by the formula, and finally we will get the partial derivation of E total with respect to O out O1. So after the putting all the values we will get the 0.74136507. Now we will propagate further backward and calculate the change in output O1 with respect to its total net input. So the formula we have this partial derivation of out O1 with respect to net O1. So we will get the 0.186 at 15602. So you can see all the formula details over the slide, so it will help you to understand how we are calculating the such thing. Let's see now how much does the total net input of the O1 changes with respect to W5. The partial derivation we have net O1 with respect to W5. So after putting all the values we will get the 0.593269992. Now we have the step number 3, that is putting all the values together and calculating the updated weight values. Now let's put all the values together. Partial derivation of E totals with respect to W5, we are getting partial derivation of E total with respect to out O1 multiplied the partial derivation of out O1 with respect to net O1, and partial derivation of net O1 with respect to W5 multiply all these values. So we are getting the 0.0821677041. Let's calculate the updated value of W5. W5 plus is equal to W5 minus eta's partial derivation of E total with respect to W5 can be calculated by W5 plus is equal to 0.4 minus 0.5 into 0.0821677041. So after calculating we will get the updated value of W5, that is a 0.35891648. Similarly, we can calculate the other weight values as well. After that, we will again propagate forward and calculate the output. Again, we will calculate the error. If the error is minimum, we will stop right there. Else, we will again propagate backwards and update the weight values. This process will keep the repeating until error becomes minimized. Now, disadvantages of using backpropagation. The actual performance of backpropagation on a specific problem is dependent on the input data. Backpropagation can be quite sensitive to noisy data, and you need to use a matrix based approach for backpropagation instead of mini batch. These are the basic 5 references I have taken to make this video, which will help you to understand what is happening over here. So we will understand today what is meant by the backpropagation, other mechanisms as well. In summary, a neural network is a group of connected input-output units where each connection has a weight associated with its computer programs. Backpropagation is a short form of the backward propagation of errors. It is a standard method of training artificial neural network. Backpropagation is fast, simple, and easy to program. A feed-forward neural network is an artificial neural network. Two types of the backpropagation networks, that is a static backpropagation and a recurrent backpropagation. In 1961, the basic concept of continuous backpropagation were derived in the context of the control theory by the J. Cayley, Henry Arthur, and E. Brisson. And backpropagation simplifies the network structure by removing weight links that have a minimal effect of the trained networks. It is especially useful for deep neural network working on error-prone projects such as image or image processing as well as the recognition. The biggest drawback of the backpropagation is that it can be sensitive for noisy data. So with these summary, I just need to thank you to all of you for watching this video.